people want to understand what CERN is, if they would just indulge me for a little bit, they'll have a clear understanding of why they're doing it, what they're looking for, and what is the potential and the facts that will come out of these experiments. CERN, and amazingly, it won't come from the scientific community or anybody who has knowledge of physics. They will not tear it apart because they understand what I'm saying. So I'm gonna make this as basic as possible. I want you all to imagine, if you want to know what CERN is doing, I want you to imagine you come into a world and you find architecture all over the place, buildings and homes and houses, and you think they're beautiful and it's really a big discovery. You find out with the houses, you can house people. You can do many things with a house, with a structure. All of a sudden, after many years, you become curious and you say, what's holding all this together? And you begin to find not nails that you can take out, but glue that has bonded itself to the materials. And you become interested in that glue that's holding the structure together. And so you're fascinated by this glue, and you've tried everything to replicate it. You can't because it's hardened. Glue is hardened. You come to the realization the only way to find out how this glue is working is to break it down to its basic particles. And you have to have that glue in its former state, not the state after it's already hardened, right? So you don't want it in the cured state, the state that you can see. You want it in its initial state, which is a liquid state, before it hardens. And so CERN, basically, is a device that will allow them to examine particles in their initial state, not after everything is bonded together. That's a very simple way to look at what CERN is doing. They're trying to find the glue that holds everything together, is what they're doing. That's the purpose of CERN. Now, what has come out of CERN is called antimatter, which was first actually produced. It was first produced in 1955. And CERN is a very old organization, but it was produced in 1955, and they found positrons, which are anti-electrons. To understand what antimatter is, I'm going to have to explain the very bare basics of what matter is. And believe me, it's going to get very weird here shortly because you're going to begin to see exactly what they're doing. But you have to understand what you're looking at now. The matter and antimatter are in fact opposites. Now, the matter that we have in front of us, if you take a piece of wood, nothing happens. It's just a piece of wood. But if you set that wood on fire, you have caused a reaction. And then it's in a dangerous potential state. It's active. If you have a battery outside of your cell phone, it does nothing. You put the battery inside the cell phone, the electrons begin to flow. The electrons will flow from one place to another. Essentially, that's what electronics are, the control of electrons. They control the direction, the speed of electrons, which create tiny pulses. They flow or don't flow, flow or don't flow. Those are called gates. Those gates form computers. And with a computer, we can do fascinating things. This is why they did, in fact, take Nikola Tesla's findings, because he discovered some things with electrons and protons that were very fascinating. Electricity within itself is a visual observation of electrons and protons in their active state, non-controlled state. Antimatter is the opposite of the matter that we can control. Antimatter cannot be controlled. In fact, when they first produced antimatter, they had to have a facility to contain it, because unlike the wood, where you have to have a reaction to cause it to burn, antimatter, you have to have a containment to cause it not to burn. That's the only way they can store it, with massive facilities to store it. Let me give you an example. In a nuclear bomb, it takes timing, which takes electronics, and the explosions have to be just right to cause a reaction. That's a nuclear bomb, like the Hiroshima bomb, which takes pounds of nuclear material. to cause it to react. And it has to be very precise. Well, let's go the opposite. Let's say we had antimatter, correct? If we had 1 gram of antimatter, that would equal about 42 or 40, let's just say 45 kilotons of TNT, which is about 4 Hiroshima bombs. And it's already inherently unstable. It's unstable. The only way to harness antimatter is to contain it. And it takes very large and expensive facilities to contain just 1 gram of antimatter. It would be a little more than a weapon. Unlike matter, which we can measure, and we can actually have a fail-safe with any explosion, because with TNT, so many grams of the components that go into TNT causes a yield or a force of an explosion. You can have small explosions like a firecracker to big explosions like C4, but you can contain that explosion, which would be called a fail-safe, right? So explosions are fail-safe. Antimatter is not. You can have 1 gram of antimatter. It can begin to react in ways that are unfathomable by the human mind. Physicists know this. 1 gram of antimatter can cause a reaction with other matter and other antimatter components that are out there, causing a chain reaction that could, in fact, 1 gram of antimatter, it is said, has the potential as the sun if it begins to react with other components of antimatter. So it's very unstable and dangerous. It's very unstable and dangerous. What they've been trying to do since 55 is control it. They've been trying to control it. They have made containment devices deep into the earth. Some have failed, some have not. If those containment devices fail, they cause megaquakes. That's what happens when they fail. Now, we're talking small, tiny drops of antimatter. I mean, just drops of raw antimatter. It's highly unstable. It has to be isolated from the rest of reality when it's contained in a literal sense. Now, given that this can be weaponized, which is true, well, there are other implications that the average person has not thought about. Our body is held together by that glue that they're searching for, that bonds matter together. Those who understand what's called the Standard Model, they have a pretty good idea of what would happen if the force table in the Standard Model is just an explanation of how all things work. You're dealing with matter and force, and they have categorized the elements of matter, everything we can touch and feel and observe, in what's called quarks, the building blocks, of protons and nuclei, and leptons, which are essentially, well, that would be like an electron. And then we have force. A force are lumps of energy that transmit the forces that bring matter to life. Like a photon, it carries the electromagnetic force. Without a photon, we couldn't produce motors or anything else. Without gluons, which carry a strong force, neutrons and protons would not be held together. In other words, the universe would not exist. And of course, you have your W and Z particles, which are for weak forces that govern radioactivity. So you have this Standard Model, and they have broken this down. But what they're looking for is a higher explanation of how everything works. This is the particle they're searching for. Now, they found half of it. They already found a component of it. That was the Higgs field. Now, the Higgs field is an explanation of they found the traces of the Higgs field. They can now observe the Higgs field. The Higgs field is what is found wherever matter is not.